When looking deep into the cosmos for galaxies that existed in the earliest epochs of the universe, astronomers turn to the extraordinary capabilities of the James Webb Space Telescope, JWST. This remarkable instrument is specifically designed to observe distant celestial objects that formed mere hundreds of millions of years after the Big Bang. One of the critical tools for identifying and studying these primordial galaxies is the measurement of redshift, a phenomenon that provides insight into both the distance of these objects and the expansion of the universe itself. Redshift, commonly denoted by the letter Z, occurs when light from an astronomical source is stretched toward longer wavelengths as it travels across the vast expanses of space. Essentially, as the universe expands, the fabric of space stretches, and the light traveling through it stretches as well, shifting it toward the red end of the electromagnetic spectrum. The greater the redshift, the farther away the galaxy is, and therefore, the further back in time astronomers are seeing it. The concept of redshift is analogous to the Doppler effect that many people have experienced with sound. For example, the pitch of an ambulance siren appears higher as it approaches and then drops as it speeds away. Similarly, light from distant galaxies shifts toward longer wavelengths or the red part of the spectrum, as those galaxies recede from us due to the ongoing expansion of the universe. By measuring the degree of redshift in the light from these distant sources, astronomers can estimate how far away a galaxy is and, in turn, look back in time to when that light was first emitted. This allows them to reconstruct the history of galaxy formation and evolution, essentially peering into the earliest chapters of cosmic history. The James Webb Space Telescope, equipped with highly sensitive infrared instruments, has proven to be an extraordinary tool in this quest. Unlike visible light, which can be absorbed or scattered by interstellar dust, infrared light can penetrate these obstacles, revealing galaxies that would otherwise remain hidden. By detecting redshifted light in the infrared, JWST can determine not only the distances of these early galaxies, but also their compositions. Infrared observations allow astronomers to detect the signatures of various chemical elements, helping to reconstruct the chemical evolution of the universe. By examining these elements, scientists can infer the processes that occurred in the first generations of stars and galaxies, including the synthesis of heavier elements from lighter ones. At this stage in cosmic history, prior theoretical models had suggested that detecting galaxies with JWST would be extremely challenging. The earliest galaxies were thought to be faint and small, composed primarily of hydrogen and helium, and therefore difficult to observe even with the most powerful telescopes. However, JWST has exceeded these expectations, revealing a surprising abundance of galaxies at very high redshifts. In fact, recent observations have identified more than 100 relatively bright galaxies that existed just after the cosmic dawn, a period when the first stars began to ignite and illuminate the universe. This discovery has challenged previous models of galaxy formation, suggesting that star formation may have been more efficient and widespread in the early universe than scientists had anticipated. One particularly fascinating finding is the detection of heavier elements, such as carbon and nitrogen, in some of these early galaxies, including one known as MOM Z14. The presence of these elements indicates that by this time, the first generations of stars had already undergone nuclear fusion and supernova explosions, enriching the surrounding gas with heavier elements. This discovery provides critical clues about the pace of chemical evolution in the universe, showing that significant processing of elements occurred relatively quickly after the first stars formed. It also implies that even earlier galaxies, composed solely of primordial elements like hydrogen and helium, must exist and remain to be discovered. These chemically pristine galaxies, which represent the universe in its most original state, are expected to be the next frontier for JWST observations. Finding them would offer an unprecedented glimpse into the conditions that prevailed before the first heavy elements were produced. The implications of these discoveries extend far beyond the mere identification of galaxies. By studying the earliest galaxies, astronomers can gain insights into the processes that shaped the large-scale structure of the universe. They can trace how galaxies grew through mergers and accretion, how the first stars formed, and how the first supermassive black holes may have emerged. Each newly discovered galaxy acts as a cosmic time capsule, providing information about a specific era in the universe's history. The ability to detect such objects at unprecedented redshifts pushes the boundaries of human knowledge and challenges long-standing assumptions about how quickly and efficiently the first galaxies formed. Moreover, the success of JWST in detecting these early galaxies demonstrates the remarkable synergy between technological innovation and scientific curiosity. The telescope's sophisticated instruments, precise optics, and location beyond Earth's atmosphere allow it to capture faint signals that would be impossible to observe from the ground. Its observations not only confirm some theoretical predictions, but also open entirely new avenues of inquiry. The detection of bright galaxies at unexpectedly high redshifts has already sparked discussions among astronomers about the need to revise models of galaxy formation and star formation rates in the early universe. The presence of heavy elements so early in cosmic history suggests that stellar evolution proceeded more rapidly than previously thought, hinting at processes that scientists are only beginning to understand. The findings also highlight the dynamic and evolving nature of cosmology as a field. Each observation made by JWST provides new data points that refine our understanding of the universe's evolution. Researchers can use this information to model how galaxies assemble over time, how elements are distributed across space, and how the cosmic web, the large-scale network of galaxies and dark matter, emerged from the primordial universe. The discovery of unexpectedly bright and chemically enriched galaxies at very high redshifts suggests that the early universe was more complex and diverse than simple models had predicted. It underscores the need for continued exploration and observation to fully comprehend the processes that governed the formation of the first cosmic structures. Looking ahead, astronomers are optimistic about the future discoveries JWST will enable. The telescope appears poised to extend the cosmic frontier even further, potentially revealing galaxies at redshifts never before observed, approaching the era of the first stars known as population 3 stars. These hypothetical stars are thought to have formed from primordial hydrogen and helium, and they may hold the key to understanding the very first steps of cosmic evolution. Detecting such objects would mark a historic milestone, providing direct evidence of the universe's earliest stellar populations and shedding light on the conditions that prevailed before the universe became enriched with heavier elements. JWST's ability to probe such extreme distances and early times promises to transform our understanding of the cosmos in ways that were once considered unimaginable. In conclusion, the James Webb Space Telescope has revolutionized the study of the early universe by enabling astronomers to detect and analyze galaxies from an era previously thought to be largely inaccessible. Through the measurement of redshift, JWST can determine the distances and compositions of these ancient galaxies, providing critical insights into the formation and evolution of cosmic structures. The discovery of over 100 relatively bright galaxies, along with the detection of heavier elements in some of them, challenges previous models of galaxy formation and highlights the rapid pace of chemical evolution in the early universe. While the search for the most primordial, chemically pristine galaxies continues, JWST has already expanded the horizons of human knowledge, bringing us closer than ever to understanding the origins of the cosmos. As astronomers continue to explore these distant realms, each new discovery will not only illuminate the distant past, but also reshape our understanding of the processes that have shaped the universe we observe today. The era of cosmic dawn is no longer a distant concept. It is now within the reach of observation, and the James Webb Space Telescope is leading the way.